Today's lecture, we will go to other representations of Fourier transform, of Fourier series. So Fourier series, as we know, there is A, B, A0, AK, B0, something like that. And we used to say if it's odd or even, sometimes A's can be zeros, sometimes B's can be zeros. This is not the only presentation of Fourier series. There are more presentations. So today we'll go through two different presentations. Like the first presentation is called magnitude and angle. The second presentation is called the convex. Okay, so today is Friday. The reading is from page 201 to 12. Next week, April 1st, Monday, the reading is from page 216 to 18. So we expect to end Fourier series by Monday. Then, in April 3rd, Wednesday, it will be exam to return. Exam to return. And also the lecture for the answers. So I will not be here. The TA will take care of this. And we will return the exam to you. We will go through the answers. And also we will post an announcement. So most likely, if you see the TA, because of any review the grades, you can see the TA during the office hours. So there will be an announcement about the office location and the office hours. Then in April 5th, Friday, the readings from page 218 to 222. Basically, we will start a new topic, which is Fourier transform. Another topic different than Fourier series, called Fourier transform. Just in summary, Fourier series for periodic signals, Fourier transform for non-periodic signals. Just like this. And also it's the due date for homework number 12. So keep in mind, in Wednesday, the lecture will not be recorded, okay? Because it's going to be go through the answers, the TA will take care of it. In Friday as well, another instructor will teach you this. So I'll be traveling, so it will be taught by another instructor. So I'll be traveling in Wednesday and Friday. So on Wednesday the TA will take care of it, and Friday the other instructor will take care of it. So there will be no recordings. I mean, the answers is fine. There's no recording. But on Friday there will be no recording as well. So if you cannot make it, please try to make your schedule to come, because it will not be recorded. And I'm willing to upload the notes by the instructor after he finished. If I cannot upload it by Friday, maybe in the following Monday, the other instructor notes will be uploaded for that lecture. I think this will be lecture number 29, because this will be 28. Today is lecture 27. Then lecture 29. Okay, then in the following Monday, I will back, so I will start going back. Then I will teach, continue Fourier series, Fourier transform, sorry. And also, we'll resume everything. Then for the MATLAB project 3, the due date will be on April 8th. Any questions? So, let's start the lecture before going to the other parts of Fourier series. There is a phenomenon that gives boundaries, and we say that, okay, this can happen anytime. So that phenomenon, basically, we know in real life it's impossible to use all terms of Fourier series, because we cannot say from k equal 1 up to infinity, right? It's impossible to say. We cannot do it. So what we will do, basically, we will use a finite. So as we mentioned earlier in several graphs, we can use n equal 10 terms, 40 terms, 100 terms, etc. So basically, we realized, or Gibbs actually, he realized that whenever we use a limited number, and that's what we can do, we cannot do infinites. Whenever we do a limit, basically there will be something called overshoots, and that overshoot is always every time 9% in the size of the jump. Okay, so what do we mean by overshoots? Let's assume we need to do a square wave, and that square wave, if we take one term, which is the cosine, so it will be like this, right? So there is an overshoot. Basically, what do I mean by overshoot? Which is the actual value. This is the actual value, and this is the value that's desired. So this is actual, this is desired. So the difference between actual minus the desired, and then the percentage, which is 9%. Okay? So that 9%, or realize like here, 1 minus 1.8, this will be divided by 2, this will be made as 9%. So this 9% jump will make, or 9% change that's going on. This is an error. We can consider it as an error, or otherwise we can call it as an overshoot. So something that undesired, which is that peak, this peak here, and this peak here. Okay? That's called overshoot because it goes higher than what I want. If it goes to a certain value rather than I want, this is called overshoot. You will use this a lot in control system in the future process. So I will go through more details about it. But this violations that we see is up to 9% if we use only one term. Then, how about if you use 3 terms? That's how the waveform looks like. And we realize the overshoot will be the same amount, 9%. Even though we are making the number of terms, increasing the number of terms, the overshoot will be the same. I'm talking about the overshoot, not the accuracy, not the distorted waveform. I'm talking about the overshoot. Then if we use 9 terms, the overshoot remains 9%. If we use 33 terms, remains 9%. So in summary, whenever we do any finite number, if you use 1,000 terms, if you use million terms, you will still get 9% error, or 9% overshoot. So that something exists, and I cannot change it. The only way that I can change it is to make the number of terms equal to infinity, and there is no way to do it. As a result, every time when we apply Fourier series, you will see an overshoot 9%. So that's called Gibbs phenomenon. That's how we recognize this. Then we say, okay, that exists everywhere. Okay? Does this make sense? Now let's go to the other presentations of Fourier series. Fourier series, other presentations. So the first presentation, which is called amplitude and phase. Representation. Basically, x of t equals to a0 is same as usual, we know it, which is the average value, plus the sum k equal 1 to infinity. It's the same, but what's half changing, which is inside the brackets. C sub k cosine k omega naught t plus phi sub k, such that ck must be like this. Okay, so what we can see that we have c and theta. ck, theta k. Initially we used to have a and b. A and b. But now we have c, and we used to have initially sine and cosine. So you can imagine it like You know that the complex numbers can be written into rectangular or polar, right? So rectangular coordinates, where is, for example, x plus jy. Polar, like z angle phi, or you can say angle phi. There's something similar to this. You can imagine like the triangle. Like here is A, K, here is B, K, then this is C, K, and here is V. Like polar and rectangular coordinates. So how is the representation? Like recall, it was x of t equals to a0 plus k equal 1 up to infinity a k cosine k omega naught t plus b k sine k omega naught t. So these two are the same, but one of them in sine and cosine, the other thing which is in amplitude cosine, amplitude angle. So how can we know, or how can we find CK, or what's the relationship between CK and BK, phi and CK and BK? What's the relationship? Basically, you can imagine it there like by looking at this term and this term, they are equal to each other. So we can say CK cosine K omega naught t plus K equals to AK cosine K omega naught t plus BK sine K omega naught t. Now how can this part equal to this part? Basically, there is a trigonometric identity for the cosine. Cosine plus angle. Trigonometric identity. So using the trigonometric identity, this yields to be CK cosine K omega naught t cosine theta K minus sine K omega naught t sine theta. This is the trigonometric. Then this yields to be AK cosine K omega naught t plus BK sine K omega naught t. Then you can multiply CK both sides. This yields to be CK cosine K omega naught t cosine K minus sine K omega naught t sine K equals AK cosine K omega naught t plus BK sine K omega naught t. So you can say, here's sine K omega naught, here's sine K omega naught t, here's cosine omega naught t, cosine omega naught t. So the remaining elements are basically, by making a comparison, you can realize that AK is actually CK cosine phi. BK is actually negative CK sine. That's it. Okay? It's just like math. Similar or rectangular, but something like AK. Now, how about if we need to do the opposites? Converts. Here we converted phasor amplitude to the regular sine cosine Fourier series. But if we need to do the opposites, if we know the sine and cosine, but we need to calculate the amplitude representation, basically we can say CK, it is actually the square root of AK squared plus BK squared. How about phi k? Phi k will be negative of tan inverse of BK over AK when AK larger than or equal to 0, or it can be pi minus tan inverse of BK over AK when AK is not 0. So this is the other relationship. So you need not to memorize it, you can write it in your note sheet. So just make sure these formulas are very important and we will apply them a lot. So, what's the proof of this? And the proof of this. Let's go number one. So ck, or let's say the square root of ak squared plus bk squared equal to square root of ck cosine pk squared plus ck sine pk all in squared. Then we can put ck as a factor here, as a square, and we take it out of the roots. Then it will be cosine squared plus sine squared. What do we know about cosine and sine? Cosine squared plus sine squared will be what? 1. So will be ck times 1, which will make it ck. And of course ck is a must, must be calculated. Then that's how we prove the first one. The second one, which is basically it's a phi k equals the tan inverse of bk over a. So let's think about it. So we have the relationship that ak equals to ck cosine phi. Then we have the relationship bk equals to ck, there's a negative sign, negative ck sine phi. Try to divide them b over and you can like multiply by negative sign, so I'm going to multiply by negative sign. This will make it positive and negative. So I'm going to say what it is. So I will say negative bk over ak. This will equal to ck over ck will cancel each other. Will be sine phi k over cosine. Or in other words, sine over cosine will make it tan. Will be tan. So we need to find phi k. So we know that here tan of phi k will be negative pk over a. So as a result, in order to find the tan, phi k will be tan inverse of negative bk over a. But the tan inverse, there is some conditions. Is it tan inverse of positive number or is it tan inverse of negative number? This is dependent on the sign of a. How? You can imagine how does the tan look like. Here's x, and here is 0, 5 over 2, 5, so the tan is actually like this. Okay, let's focus more in this period between negative we need to say, look at the tan inverse. Tan inverse, basically, you will flip the axis. Here is x, here is tan inverse of x. So we will flip the axis. X-axis will be y-axis, y-axis will be x-axis. So here's pi over 2. Here's negative pi over 2. So here, what matters with us, are we in this region or in this region? So this region will be number 1, this region will be number 2. So we can say, number 1, if between negative pi over 2, pk, actually I would say this region of the upper if theta between negative pi over 2 to pi over 2, or in other words, between negative 90 degrees to 90 degrees, we can say pk will be tan inverse of negative bk over ak, such that in this situation ak larger or equal to 0. The second thing, which is if pi over 2 pk larger than pi over 2, at the same time will be 3 pi over 2, which means it is between 90 degrees to 270. So we will say that pk will be pi plus tan inverse of negative bk over ak, such that here ak is negative. So here with this situation, you see these two periods. The first period, number 1, when it was between negative 90 to 90, number 2, when it is between 90 to 270. Okay, so what will happen between 270 to 360, or the remaining? It is already been included here. How? You can imagine it like this is a circle. When we go from negative 90 to 90, go from here to here, this region 1. Then when we go from 90 to 270, this is region number 2. Yeah. Because this is 0, 90, 180, 270 degrees. At the same time, if you want to talk about the negative, this is 0, this is negative 90, negative 180, negative 270. That's how we can do it. So as a result, we got two formulas. I mean, the term can be depending on if AK is positive or if it is negative. If it is negative, you will see pi plus tan inverse. If it is positive, then we will say tan inverse. So the point is just using this pi, depending on if it is negative or positive. Okay? Now, using this relationship, the convergent here and convergent here, we can convert between amplitude and phase representation easily. If you need to do Fourier series, find A and find A, B, A's and B's. Then after that, if you need to convert this to amplitude and phase, just do these equations. And that's it. So that's the best way. Solve it as what you used to do. Then do the conversion using these equations. Any questions? Someone can say, what's the point of this representation? We already used A, B, A0, AK, BK, and they are working fine, right? Why do we need to switch to the other thing? The answer is there's something that you will see a lot later in what's called spectrums. I'm not sure if you're familiar with a device called spectrum analyzer. So the spectrum, basically, it will be easy to do when you plot this related to the amplitude and phase shift of the Fourier series. So we will use CK. So CK is actually the amplitude of the spectrum. Okay, what do I mean by spectrum? How it looks like? Basically, you can say this is the frequency, this is CK. We know the frequency as omega over 2 pi, or in other words, 1 over the period. So we can say for a certain amount of signal at f0, this is the magnitude. At 2 times f0, this is the magnitude. At 3 times f0, this is the magnitude. And so on. How can this be beneficial for us? So basically, here, CK is combining. AK and BK. So we can see the frequencies. Spectrum. How can this be beneficial for us? This is actually very important in some practical applications. What's the frequency of the frequency and the voltages of the wall atoms? What do you think? The frequency and the voltage. 60 Hertz, how are the voltage? 120 volts, RMS, right? And so it will be cosine, right? 60 Hertz. So it's cosine according to Fourier series in our standard. I'm going to write it this way. Which is, we say 120 square root of 2 cosine 2 pi times 60 t plus, let me see, the angle is 0. Right? That's how it looks like, the voltage. According to Fourier series, in the spectrum analyzer, it is cosine, right? So this is C, right? And the frequency of 0 is 60 Hertz. According to the spectrum analyzer, then it will be at 60 Hertz, it will be 120 square root of 2. That's the only component that you will see. Is this correct? That's what it should be, according to our spectrum. Yes.
Say you can also purchase allowance for it. That's not very.
Anyway, so let's talk about here the frequency and the magnitude. So C, 120. Yes.
Is the frequency the way, is that angular frequency or is that like F?
Here I used F as 60 Hertz.
Okay.
Just 2 pi factor. But I mean, I'm making it like as F, not as omega, just to make it more convenient for us. So when you see here, that's what's supposed to be, which is CK. Like that this way. When you do the spectrum analyzer, we have some oscilloscopes that can give the spectrum analyzers, or some devices that we have, that can be spectrum analyzer of the waveform. But when you do it on the device that you have in the lab, do you think you will get a pure signal like this? I don't think so. Why? Because the signals that we have is not 100% clean. What do you mean? It's not 100% 60 Hertz or instant because there's some other equipments inside the signal. These equipments can be low, they might not be doing this. So, most likely, whenever you do, if there is something, the signal is not pure enough, so you will see at 60 Hertz high, at other frequencies low values, very low values, and at the fundamental or at 60 Hertz is high. Since 60 Hertz, that's what we want, the desired. This is something we call it the fundamental frequency, or the frequency that the desired, that's what we need to do. But whenever we deal with these spectrum or different frequencies, or whenever the signal or the real life not 100% accurate, then we will have some other parts. This thing we call it fundamental. The others we will call it harmonics. So here like 2 times F, 3 times F, etc., 4 times F. These harmonics are something undesired because we would like to make the signal pure cosine without any disturbance, anything wrong with it, right? So we would like to be the ideal case. While here it's in real life, they are not everything is ideal. So we need to try to do something called filter out these harmonics. There is also something that you will discuss it later in communications, like low pass filter, high pass filter, band pass filter. Basically, we would like to pass only the desired thing or the fundamental thing, while the others are harmonics. Okay. Yes.
Could we include like is this how like Afternoon could like put a byte of information into that and then transmit it at the same time?
Yeah, in communication it can be, but here I'm talking about overall. In power, maybe on something like the power device, this can be challenging. So how can we make sure that to do this or to get this frequency? Basically, we can do some filters. Some passive filters, active filters, low pass, band pass, mid-band filter, whatever. There are different types, first order, second order, third order filters. Or the other thing, what are the sources of these harmonics? We know the power is being generated from the generator. The generator will produce a sinusoidal waveform, which is cosine. What are the sources of these harmonics? What do you think this comes from? Any thoughts? Yes?
Random capacitance and inductance and services.
Like you can imagine the capacitance and inductance as 1 over j omega c or j omega l. So, do you think they will change the frequency? Basically something that causes the frequency. So, there is, yes? Resistive, I don't think so. There is something changing this. You are very close to the answer, which is basically something related to the load. So the loads can make some harmonics. What are these loads? We have some ohmic loads, which is Ohm's law can be applied. What are these loads, ohmic loads? Resistor, inductor, capacitor. These three are working well. There's no problem with this. Our challenge is with non-ohmic law, where Ohm's law does not apply. Like what? You know electronics, diodes, transistors. You know rectifiers, which is, we used to use it from AC to DC converter, right? And we used it a lot. We used it in cell phone charger, we used it in laptop. Whenever there is a rectifier, this will cause some harmonics. Whenever there is a nonlinear elements, this will cause harmonics. So actually, your cell phone has an impact pact on the charger, impact pacts on the power. Any electronic device has an impact pact, a bad impact. Okay? So these electronics causes problems. These problems causes harmonics. However, there are some conditions like if the harmonics does not exceed 3%, then it can be accepted. If it exceeds 3% of the fundamentals, then we need to take an action. So electronics creates harmonics, creates something that undesirable. How to solve it? Because sometimes electronics. Electronic causes the problem. I can solve it by using other electronics, by creating something we call it active filters, which is basically based on op-amps and different parts. Or you can use passive filters using LCL filters, or L filter, or LC filter, whatever. So there are several types for it. But sometimes the problem is because of electronics, the solution from the electronics as well. Other sources of the harmonics, there are renewable energy sources. How? The photovoltaics is being generated electricity based on DC. Right? We need to convert DC to AC, so we can use it. Right? To convert DC to AC, I'm using electronics. I need to use inverters, which is based on MOSFETs or transistors, or IGBTs, whatever. Then, when you convert this or when you use electronics devices, then you are creating harmonics. So the renewable energy sources interaction with the grid causes problems. How to overcome this? We used to use filters. These filters associated with the renewable energy can elevate with these harmonics. Okay? You can imagine that you're putting water into the water. Just put more water, but you need to make sure it's clean. We need to purify it by adding a filter. Then also some other thing, which is like the wind energy as well. The wind speed related to the frequency. When the wind speed is changing, this will affect. So I don't want to go far, but I'm just here. I'm telling you that about the importance of using CK, or CK basically for the frequency as indication. So whenever you need to see a pure signal, look at the harmonics and compare it what you're supposed to be. So is it like the fundamentals, or is there any changes? And again, you can use this and tell me about power area, or you can do more in communications and wireless. So this is CK. How about Phi-K? Phi-K is the fifth spectrum. And you will see like the phase as F0, for example, 2F0, 3F0, etc. So, for example, it must be bounded between pi to negative pi. Okay? Then maybe you can make it later omega, which is 2 pi times f. Then maybe we can do more or discuss more something related to pi plots. Not now, maybe later. Okay. Any question about this presentation? Let's go to the next one. Second representation, which is complex exponential representation. So the complex exponential representation is k of t, up to x of t, equals to the sum k equal negative infinity to infinity. Keep in mind we're starting from 0, from negative infinity to infinity, x sub k e power j k omega naught t, such that, or where k xk sub k will be 1 over t, the integral from 0 to t, x of t e power negative j k omega naught t dt, or in other words we can say 1 over t, the integral from negative t over 2 until t over 2, x of t e power negative j k omega naught t dt. And most likely we will use this, x sub k. So the good point about the complex exponential, there is no a, b, c, or a naught, ak, bk. There is only one, which is x. So xk. There is something here which is, we will not say from k equal 1 to infinity. We will say equal from negative infinity to the infinity. So it can be any negative number. K can be negative 1, k of negative 2, negative 3, up to 1, 2, 3, 4, etc. So these two important things, no more AK, BK, CK, A0. Here we have only one, and we have K equal to negative infinity to infinity. This is something important. The difference between this and the others, just good say from K equal 1. From negative to infinity. Okay, where does this come from? Recall Euler formula. Euler formula says e power j theta equals to cosine theta plus j sine theta, right? So basically, if you apply Euler formula here, you can get an idea how we can find A and B. Okay? So I'm not going to go through the derivation, this will take no time, but here just I want to let you know, by applying Euler formula, you can go to the other part, or the other representation. In summary, for this representation, the complex representation, basically, you will use x of t equal the sum from k equal negative infinity to infinity, xk equal jk omega t, such that x of k 1 over t, the integral from negative t over 2 to t over 2, x of t equal negative jk omega naught. So, as a small case, how about if we assume k equals 0, it will be 1 over t, the integral from negative t to 2 over t over 2, x of t e power 0 will be 1 dt, so it will be the same as a0, which is the same as average value or in other words, DC components. So the best thing, or the good thing about this representation, I don't need to put A0, I don't need to put A and B, all of them in one term, such that A0 just substitutes K equals 0, and so it will be X0 the same as A0. Okay? The other X's you can find them based on your analysis. Okay, any question about this representation? Okay, so there is an important table 5.3 in page 206 about this using Fourier series complex exponential representations. So because now they will have different tables, because recall in the Fourier series we used to have this table, but this one is written into sine and cosine form. How about if we need to have a Fourier series written on the complex form, which is this table? Table 5.1. Here's the summary. So there will be another table, but let's look at the table here about the changing, then I don't have maybe the other table, but I can go over to you soon. So here is this table, summarize the three different things. Okay? Sine, amplitude, and exponential. I don't know where's the other table. I should have the other table about Fourier series in the exponential representation, complex exponential representation. Anyway, I will see it in the textbook and can write it together. Okay, so again, this is the table. We know the cosine sine representation, we know the phase amplitude representation. This is the complex exponential, or sometimes they can call it exponential representation. Let's do an example. Assume we have a pulse train and we need to do Fourier series using the exponential. Fourier series exponential. So that pulse train, the waveform is given as here's here's 0, tau over 2, negative tau over 2, here's the period, t over 2, negative t over 2. Then we have another pulse here that's centered at t. Another pulse here that's centered at t. So keep in mind the period between t over 2 and negative t over 2. So the period is not only this. The period is the whole. All of this between t over 2 and negative t over 2. So the total will be t. Or in other words, I can say t over 2 minus negative t over 2 equal to t. So this is the whole period. One period. Okay? So in that period, we will keep in mind during that period, x of t will be equal to a if t bounded between negative t over 2, t over 2, for one period, or 0 otherwise. Okay? Now, we need to do the Fourier series. Fourier series exponential, x of t equals the sum from k equals negative infinity to the infinity x sub k e power j k omega naught t. Okay? Then what should I do? We need to calculate first x sub 0, which is 1 over t, the integral from t over 2 over t over 2 x of t e power negative j k omega naught t dt. Okay? Now let's substitute. It will be 1 over t. The integral from negative t over 2 until negative tau over 2, 0, equal negative j. Okay, omega naught t dt, which is this area, this area, this area, this area. So it will be 3 parts. So this is 1. Then plus the integral from negative tau over 2 until tau over 2 of a equal negative j. Here k is 0, 0 omega naught t dt plus the third area, which is the integral from t over tau over 2 over until t over 2, 0 equal j, 0 omega naught t dt. So this is 0, this is 0. The remaining thing, the remaining elements are 1 over t, the integral from negative tau over 2 until tau over 2, and equal 0 will be 1. So it will be 1 dt, which will make it a over t, then tau over 2 minus negative tau over 2, which will make it tau. So the answer will be a over t tau. This is x of 0. Okay? Understood? Keep in mind, x of 0 is the same as a0 because it's DC components. Any question? Now we just calculated x0. How about x of k in general, no matter if it is 0 or not? So x sub k equals 1 over t, integral from negative t over 2 until t over 2, x of t equal negative j k omega naught t dt. So we will not substitute k as 0, let's make it as, keep it as k to find the general expression, no matter what k is. So which will be 1 over t. So we said between negative, the integral from negative t over 2 until negative tau over 2, this is 0. So don't worry about it. Then the integral from negative tau over 2 until tau over 2, this will be a equal negative jk omega naught t dt plus the integral from tau over 2 until t over 2, this is 0 as well. So don't worry about it. These two are zeros, remove them. So the end, at the end will be 1 over t, and I can put a outside of the integral, will be a over t, the integral from negative tau over 2 until tau over 2, equal negative jk omega naught t dt. Then how to do the integral of the exponential will be 1 over t times 1 over negative jk omega naught t, then equal negative jk omega naught t, substitute for t equal negative tau over 2 until tau over 2. So let's keep going. It will be a over negative jk omega naught t upper. Then the integral, which is substitute tau over 2, it will be equal negative jk omega naught tau over 2 minus equal negative will make it positive jk omega naught tau over 2. Okay? So far so good. Now what I'm going to do, I'm going to multiply by 2 over 2. Let me multiply by 2 over 2, it will be as 2a, and recall 1 over negative j equal to j, or 1 over j equal to negative j. So I'm going to just remove this up. So it will be 2a times j over k omega naught t. Let's see here, then e power negative jk omega naught tau over 2 minus equal jk omega naught tau over 2 divided by 2. Okay. I think, yeah, I need to do something. Let's recall e power j theta equal cosine theta plus j sine theta. Then e power negative j theta equals to cosine theta minus j sine theta. Subtract then e power j theta minus e power negative j theta equals 2j sine theta. Therefore, sine theta will be e power j theta minus e power negative j theta divided by 2. Now I need to convert this something similar to this. They are not ready yet. So I need to include the j. So I think it's not a good idea to move the j there. Let's keep the j. I will move all the j inside. So it will be negative j. I'm just going to finish soon, so negative j. So I will put the negative other side equal to 2a divided by k omega naught t. Then the negative sign will inflate the plus side in the e power jk omega naught t minus e power negative jk omega naught t divided by 2j. This is sine, so it will be 2a over k omega naught t sine k omega naught t. So let's stop here and we'll continue next lecture.